Today, we're going to get into the hardcore chemistry, but we have to do this in order to explain the problems with origin of life. I can't keep this just 30,000 foot level, and because that's where people get confused and they make all sorts of mistakes. You remember that Kruger-Dunning plot, that if we don't know very much, we end up becoming very confident in our claims. But it's when we start learning more, we see all the problems that arise here. And so I really need to get into some of the details. So the reason for this lecture series in Abiogenesis, if you're just joining us for this, if this is your first lecture, Dave Farina posted a video entitled Elucidating the Agenda of James Tour, a Defense of Abiogenesis. You can see the description box below for the link. After that video, I was confused about almost every slide and statement that Dave Farina presented. There were numerous gross scientific inaccuracies in his claims, in my opinion. Some others might be likewise confused, and I will use the Farina video with timestamps as a launch point for this series of lectures. So you'll see it might say like 8.23. That is at 8 minutes and 23 seconds. You could go to his video and see where he said that. I'm thankful to Dave Farina, thankful that Dave Farina attempts to teach the layperson about scientific topics on his YouTube channel. Professor Dave Explains. That's a commendable endeavor, and I therefore seek no contest with Dave Farina, only clarification. I just want to be his friend. I really do, and I wish he would have just reached out to me, sent me an email or called me. My number and my email are right there, and we could have spoken this thing out. But anyway, I'd be glad to talk to you, Dave, now, anytime. Be glad to talk with you. And if you're ever in Houston, I invite you to come and visit me. Other synthetic chemists can comment and point out where I'm correct or incorrect. I particularly invite a critique from my synthetic chemist colleagues and students studying synthetic chemistry and those studying origin of life. If you're disputing something I have to say, please provide a reference so that I can check the thing out and try to understand it better. Let's look at enantiomers and chirality. Any molecule or object has a mirror image. Congruent molecules, all atoms and bonds in a molecule, can be superimposed on the mirror image. So you can have two molecules, and they can overlap. They can be mirror images, and then you can turn them and overlap them. Most objects are like that. You look at the mirror image of an object. So say we look at the mirror image of this beaker, this mug, and look at the mirror image, and the two will be identical. They would be able to overlap. Of course, not the writing on it, but the structure itself. And most objects are like that. There are other objects that have non-superimposable mirror images, like my left and my right hand. If I put my left hand up to a mirror, I'm going to see my right hand in that mirror. I'm going to see what looks like my right hand. And so the two images are non-superimposable. So these are mirror images of each other, but they're non-superimposable. That's why I can't put my left hand in my right-handed glove. It doesn't fit right. So the vast majority of biological molecules are like that. They have a non-superimposable mirror image, which makes it difficult to synthesize them. Even today, we know how to do it, but it's difficult. You have to figure out how that might have been done on an early Earth. Enantiomers and chirality. Some molecules, such as 2-butanol, are not congruent on their mirror image. And here's a molecule. It's like handed. I mean, you try to overlay them, and they won't be able to be overlaid. They're non-congruent, and they're mirror images, like my left and my right hand. Molecules that can exist as enantiomers are said to be chiral. It's a CH, but it's pronounced like a hard C. Chiral. Chiral means handedness, hand or handedness. If the mirror image is congruent, i.e. superimposable, the original structure is achiral. Some macroscopic objects, including hands, screws, baseball gloves, these are chiral objects. Many chiral molecules contain one or more asymmetric carbons, often called a stereogenic center. An asymmetric carbon is a carbon with 4 different groups on it. So when you have a carbon atom with 4 different groups on it, it's going to be chiral. It's going to be stereogenic. It's a stereogenic center. It's an asymmetric carbon. Whether the molecule itself is chiral depends on whether it has a mirror image or not. An internal mirror plane or an internal point of symmetry. An asterisk is a convention used to denote an asymmetric carbon. Most chiral molecules contain one or more asymmetric carbon atoms or stereogenic centers. However, an asymmetric carbon atom is not a necessary condition for chirality. You can just have a helix, and that would give you chirality. For a pair of chiral molecules with more than one stereogenic center to be enantiomers, they must have opposite configurations at every stereogenic center. So here now you have 2 carbon atoms. Each of these carbon atoms has 4 different groups on it. So this carbon atom has a OH, a methyl, a hydrogen, and another carbon bound to it. This carbon has a hydrogen, an OH, and a carbon group in this direction, different carbon group in this direction. This is 2,3-pentane diol. It has, when you have 2 stereogenic centers, there's up to 2 to the n isomers, where n is the number of stereogenic centers. So if you have 2 stereogenic centers, you can have up to 4 possible isomers. And here are the 4 isomers. So when you have 2 stereogenic centers, now you have to control 4 possible isomers, 4 possible configurations from just these 2 stereogenic centers. And how do these compare to one another? Well, this pair and this pair are enantiomers. They're mirror images of one another. This pair and this pair are enantiomers. And all other correlations are what are called diastereomers. If they're not enantiomers, then they have to be diastereomers. All right, or if they're not the same. All right, if they're not equivalent compounds, but they're still isomers of one another. They're still constitutional isomers. All right, resolution or separation of enantiomers. How is that done today? How do we do that today? Well, the separation of a racemate, that means an impure material where you have both the right-handed and the left-handed into pure enantiomers. This is how it's done. It's a problem because enantiomers have the identical melting point, the identical boiling point, and solubility and the same solubility, so making the separation a non-trivial task. The resolution of enantiomers takes advantage of the fact that diastereomers, unlike enantiomers, have different physical properties. The strategy: convert the mixture of enantiomers temporarily into a mixture of diastereomers. Resolving agent: an enantiomerically pure chiral compound used to form diastereomers from a racemic mixture is called a resolving agent. There are common methods of resolving in a laboratory: chiral chromatography, diastereomeric salt formation, selective crystallization. All of these are difficult, and they have to be worked out for each new class of compounds and for each compound. And it's a lot of work separating enantiomers. In selective crystallization, a solution of a mixture of enantiomers is cooled to supersaturation, and a seed crystal of the desired enantiomer is added. The seed crystal serves as the resolving agent and promotes crystallization of the desired enantiomer. This process is often performed on large scale by the pharmaceutical industry. It's not easy, and they have to keep everything absolutely pristine, because you can get a lot of the wrong isomer crystallizing out if you're not careful. Yeah, there's other questions of what are called polymorphs. In any case, at 4035, some think, quote, there are other ways to get an excess of L-amino acids, unquote. Quote,
it has been demonstrated that recrystallization of a mixture of amino acid racemates with a slight excess of asparagine caused amino acids with the same configuration to preferentially co-crystallize. You get a solid containing only one enantiomer and a supernatant primarily of the other. All that's left is some natural filtration mechanism to separate the two and the emergence of autocatalysis in one.
That's what was said on that video talking about how much is known in origin of life. It has been demonstrated that the recrystallization of a mixture of amino acid racemates with a slight excess of asparagine, and I want you to remember that slight excess, cause the amino acids with the same configuration to preferentially co-crystallize. You get a solid containing only one enantiomer with a supernatant primarily of the other. That's not exactly right, as we'll see. So that was a gross extrapolation. But this was the only place in that whole video where a reference was given. The article was shown that I could reference and pull that thing out when it came to a chemical reference, chemistry. The only thing. So I was able to go back and look at it. And then there's this statement, all that's left is some natural filtration mechanism. Never offered what that meant. What is a natural filtration mechanism? Maybe you can share that with me. To separate the two, an emergence of autocatalysis in one. How did autocatalysis emerge? I'd love to see that. And so one can over-trivialize things. And it makes it seem like, oh yeah, sure, that would be really easy to get homochirality. Let's look into this. Homochirality equals 100% enantiomeric excess, meaning that you have 100% of one enantiomer. In these articles, because the physical properties of enantiomers are identical, they seldom can be separated by simple physical mechanisms, such as fractional crystallization or distillation. It is only under the influence of another chiral substance that enantiomers behave differently, and almost all methods of resolution of enantiomers are based on this fact. That's from this reference that's shown below. Louis Pasteur experimented with tartaric acid-derived salts. Pasteur noticed that crystals of tartrates had small faces. Then he observed that in racemic mixtures of tartrates, half of the crystals were right-handed and half were left-handed. And he painstakingly manually separated these. In solution, the right-handed compound was dextrorotatory, meaning it turned light to the right, plane polarized light, and the left-handed one levorotatory, turned plane polarized light to the left. Pasteur determined that the optical activity related to the shape of the crystals and that an asymmetric internal arrangement of the molecules of the compound was responsible for the twisting of light. That was a fortuitous discovery by a man who noticed absolutely every detail. Very few compounds would separate like this on crystallization, show these different structures, and they don't spontaneously separate. Pasteur himself had to separate them. All right, so here's an article, a recent article from 2014. Are racemic crystals favored over homochiral crystals by higher stability or by kinetics? Insight from comparative studies of crystalline stereoisomers. What they write is, the predominance of racemic crystallization over the formation of a conglomerate of homochiral crystals from a liquid or non-equilibrating enantiomers is an outstanding unexplained fact in organic solid-state chemistry. So that means that the vast majority of crystals don't segregate when they crystallize into different enantiomers. The vast majority of them co-crystallize. It is more stable for them to co-crystallize. And it says here, racemic crystals are predominantly, but not exclusively, more stable and more dense. Denser crystals are predominantly more stable, but there is no quantitative correlation between density and energy difference between partners in the chosen pair. So some people say 9 out of 10 co-crystallize and 1 out of 10 crystallize. And he says there's really no quantitative statistical basis for that. I don't know that anybody's really done a careful study of that. But in any case, it is a rare thing that they will crystallize separately. Here's the paper that was cited in that video. So here's a screen print from that paper, and from this I could see the authors' names, and I could get the publication and look this up from that journal. So I looked up this article. So when I went to that article, I looked it up, and here's a copy of that article. As it turns out, it's not quite like it was displayed to us in that video. For example, it says here, which I called it out here, As a typical example, we dissolved DL-valine 600 mg and DL, that means the racemic mixture of asparagine, monohydrate, in 10 milliliters of water at 100 degrees. So if you look at that 600 mg to 2.1 milligrams, this is a 350% by weight, 273% by mole excess. So that's not just a slight excess of asparagine, that is a large excess, 350% by weight excess. Remember you said a slight excess? It's not slight at all. Finally, if you look at this call out, you see here there's a 2,700% by weight. So again, this is 2,700% weight excess. So you have to have a homochiral compound and use a very large excess of it to get another amino acid to co-crystallize selectively as one enantiomer on top of that. But then you read this article and you try to figure out how efficient is this process. Because the way it was portrayed to us in the statement is this is highly efficient. But this is what happens when you really try to dig into an article. Remember that what was said is a solid containing only one enantiomer and a supernatant primarily of the other is simply not true. This is what was stated in that video. But because you try to figure out what is the yield here, what is the amount, how efficient is this, and you can't find it. It's nowhere in this article where you can find out the efficiency. Sometimes articles are written in a way that it obscures information. You say, well, why didn't the reviewers catch this? As a reviewer of many research, I'm sent many articles per day to review, and I don't accept them all because I wouldn't be able to keep up with the rest of my life if I did. But you get reviewer overload, so you can't check every detail. It's only when you really start studying this paper that you see that they never told you the efficiency of this process. And this is what happens, and when they don't tell you the efficiency, it generally means it's not very efficient. Well, anyway, the authors, this Kojo et al., cited one of their earlier papers in 2001. So this paper is from 2004, but they cited a 2001 article, so I went and I looked up that article. And here's that article. And this is what happens when you get an article and you really start tearing into it. And so this is just a copy of an article that I printed out. And this is just a copy of the notes that I had written on it as I'm trying to follow their actual chemistry. I don't just read the abstract. I'm trying to follow the chemistry. It's hard to follow the chemistry. Even for a trained scientist, it's hard to follow the chemistry and track this thing down. But I'm looking at it and trying to track it down. So here's a cleaner copy of it. And here's what you find. They used a 700% excess of asparagine was used, not a slight excess as was claimed. And then here's a quote from this article, quote, less than 1% of the mixed asparagine phenylalanine crystals consisted of phenylalanine, and the maximum EE of the phenylalanine was 22.3%. So in other words, less than 1% of the crystal that formed of asparagine contained phenylalanine. That's not the way it was portrayed in that article. Less than 1% of it. So you have 99% asparagine and less than 1% of the thing that you wanted crystallizing on it, phenylalanine. And you don't know what less than 1% means because he should have told us how much, but he just said less than 1%. Less than 1% could be 0.1%. It could be 0.01%. It could be 0.00001%. We don't know. But when an author writes less than 1%, it just means it's terrible. But he never told us how bad. And then its EE was 22%. Remember, homochiral is 100%. Its EE was 22% EE. So he said you get, what that video had said is that you get one enantiomer crystallizing and predominantly the other enantiomer in solution. But no, it's not one enantiomer. It's just 22% EE. So there's a lot of the other enantiomer as well. When you're less than 100% EE, the other part of that is the second isomer. And so It's only 22% E and only less than 1% of it. How much less than 1%? And what is the average EE? He says the maximum EE was 22%. What was the average EE? Not the maximum EE. Because the average is the average of what you'd get. So in other words, he ran this multiple times and the highest he ever got was 22%. Was the average 2% EE? We don't know. At 1% phenylalanine in the mixed crystal with asparagine, that is 0.41% to 1.6% yield of L-phenylalanine at a maximum of 22.3%. So how efficient is this process? The only thing that I could calculate is that his yield is 0.41% to 1.6% just using the spread that he's telling us. And here's how I calculated this. So if you chemists would like to go in and see how I calculated this, that I'm not just throwing out numbers at random here. And if I calculated something wrong, let me know. I couldn't be that far off. And so you see here, his yields are really low. This is not an efficient process. So when it was said at 40 minutes and 40 seconds,
you get a solid containing only one enantiomer and a supernatant primarily of the other.
Is a mischaracterization. The supernatant is even more messed up than this. Because 99% of it is still in the supernatant. So this is a terrible reaction. But it was portrayed as being really good. That's what happens when you get into the details of this. Based on the Kojo et al. Work, some suggest that
all that's left is some natural filtration mechanism to separate the two and the emergence of autocatalysis in one. This is one way that a slight asymmetry can be dramatically magnified.
And so all of a sudden, in that video, the whole problem of homochirality is solved. Just like that. It's solved. Not solved. I wish I had a reference on the autocatalysis so I could study that. Maybe that was mischaracterized. I wonder if there was a mischaracterization of that data as well. Did it start with something that was 22% EE, with less than 1% of it enclosed within the crystals of 99% of a different compound? So you have 99% of compound A, and only 1% of that is your compound B. That's only 22%, only 22% EE, which means that it's far, far from homochiral. And is that what your reference on autocatalysis started with? And I'd like to see that autocatalysis to really see what happened. How much operator interference was necessary to make that happen? Was it in a pristine laboratory with clean glassware and expert students? I mean, it is fallacious to make claims like that and to throw it out like that solves the chirality issue. I'm telling you, every slide in that video, I'm not coming against a person, every slide in that video was like this. Every slide. And we're going to dissect it and go through the slides of that video and just show the problems. But every slide was like this. It was, they're that wrong. They're that wrong. Yeah, that wrong. Summary on homochirality. Enantiomeric resolutions are difficult experiments to execute. There is massive human involvement in the experiments. The interpretation of the data is not trivial for the researchers, and it's not a clear presentation of the data. The interpretation by the reader is made all the harder by the insufficient data provided by the Origin of Life researchers and by the way they present the data. It can be hard to understand scientific research articles, especially for the layperson. So when the layperson tries to understand these articles, I don't think they can understand it. I mean, it took me a while to try to follow this, and I had to do this tracking game to go to other articles to try to ferret this thing out. It's not easy. The layperson often does not have the expertise to properly interpret the data for herself, and therefore her descriptions and contextualizations suffer. So she relies on the press descriptions, which can be inaccurate, as we've seen. Making single enantiomers is one of the hardest problems for all synthetic chemists, not just those doing Origin of Life research. This is hard chemistry. It has not been solved in prebiotic research. It is difficult to solve in everyday life for chemists. It's never an easy thing, but it can be solved. It's not easy. But now synthesizing molecules that have a lot of stereogenic centers where they very rarely have a mirror plane. So if you have 10 stereogenic centers, which is just a few, then you have 2 to the 10th possible isomers. There's a lot of molecules that will have 100 stereogenic centers. A lot of macromolecules with 100. So you have 2 to the 100th. That's a big, big number. And there's some that have much more than that, so that you get close to numbers that are like 10 to the 90th, which are the number of elemental particles in the universe size numbers. How do you get those controlled? It's hard. It's hard. We have no idea. That's why I say we remain clueless on the origin of life. It's not that we lacking certain pieces of information. We remain clueless. All right, well, we'll come with another video. The next video is going to be on carbohydrates. I'm just plowing through these. This is why I'm still in the same shirt and the same tie. We're putting these out on different days, but I'm just doing a marathon right here and plowing through these videos so that you know the next videos come out. And the next video is going to be on carbohydrates. That's the hardest class of molecules to think about how they might have been synthesized. The hardest class. Okay, thank you. Thanks for joining us. If you want to subscribe, just click right here, subscribe, and we'll give you a shout out when the next video in this series comes out. Thank you.